the research I'm doing as part of the Green Carbon project. It's mainly about producing char from biomass and then using it to remove contaminants from water. It's here at Aston University in the UK. So I will give a small introduction and motivation for the work I'm doing, talk to you about the research objectives related to that, how I'm doing the experiments and how I'm then applying the char I produce, tell you a bit about the results I'm getting, and then some conclusions and the work I'm still doing and need to do. So as an introduction, we all know nowadays the waste problem is very big everywhere in the world. So we have lots of different wastes. Some of them you can recycle, you can use for some other things, but some wastes are just waste. You have nothing you can do with them. So that's a problem. Traditionally, wastes can be burned. That's useful to getting energy. They can be landfilled, which is the worst option possible. Is just disposing of it, and it's becoming a huge issue in lots of countries. There's lots of legislation coming up about that to forbid landfilling, which is very important that it happens. Of course, if you can recycle, you do it. Some waste you can do that. And then there's other options like fermentation, composting, and using it in the soils, depending on the waste, of course. So when you have this waste and you, for example, landfill, situations like this can happen, which is can lead to catastrophic situations. And besides air pollution when you're burning it, you can also contaminate water streams when you're landfilling, or you create a waste stream from your waste disposal. So there's both the issue of the waste accumulation and contaminating air and water streams. So we have this double problem. So there are some advanced technologies that can be used to convert wastes, and there's lots of research on it. There's gasification and pyrolysis, which is what I'm going to talk about. So pyrolysis has been around for a very long time. Evidence of charcoal used for paintings in caves in prehistoric times was found, and charcoal comes from the pyrolysis process. It was not made on purpose, but it comes from there. The charcoal is used for cooking and heating, and traditionally, and still nowadays in many places, you just make a pile of typically wood or waste agricultural residues, and you increase the temperature by burning the outside, and you make the charcoal on the inside. So that's how in many alternatives is still done like that. And now there are advanced reactors for pyrolysis. So briefly, pyrolysis, you take a material which can be waste biomass, you put it into a closed vessel, reactor, a space with limited or no oxygen inside, and you increase the temperature, and then you obtain gas, liquid, and solid products with different qualities and distributions. So the gas product is in many options burned to get energy for the process itself, for drying biomass. The liquid is this viscous, usually mobile, dark brown liquid, also used to getting energy and potentially some interesting valuable chemicals. It's been used already to get flavoring compounds. And then the char is this black, mainly carbon material that you can also burn. If you do that, you call it charcoal. You can use it in the soil. You call it biochar if you do that. You can use it to clean water and gas, which is what I'm going to talk about more specifically in a bit. You can use it as a catalyst for building material, lots of options. And these three products in pyrolysis, depending on the conditions, the reactor, and the materials you start with, will have different distributions and different quality, of course, depending on temperature, on the residence time of the solids, on many different aspects. So as I said, the char is my main focus. So I have here a picture of one of the chars I produced. It has many applications to get energy, to apply it in the soils, to purify air. Traditionally, those gas masks from the war used a form of char called activated carbon, and it's still used nowadays. Also to clean water, this material is used, and many other applications. And the one I'm focusing on is decontaminating water. So we can see here an example of a water that was contaminated with a dye or red dye, and then char or char-derived material was added, and that was absorbed on the char's surface, and the dye disappeared. The water can be cleaned in this way. So this is very important, and usually in the industry, you use a material that's related to char, but it's not exactly just char, it's activated carbon. And this material is the main adsorbent used worldwide. Its market is increasing still because there are many legislation coming up to prevent and to reduce gas emissions, especially in developing countries, in China, India. So there's a market for these kinds of materials, and you can use it as for liquid phase applications or for gas phase applications. And it comes in different shapes, forms, powder, granular, extruded, and different ones. So usually, to get the activated carbon, you can either take a char or you can take the precursor itself, biomass, and you use an activating agent. You use steam or CO2 as the atmosphere to treat it, and you expose it to high temperature again. It's often 2 steps, which means you do the pyrolysis first, and then you do the activation step. So that's time consuming. And usually in the industry, the feedstock you start with is coal or coconut shells, and this is not very good because available everywhere, they're not abundant. So there's a lot of research now trying to find suitable alternatives that can be cost effective and perform well for these kinds of applications to clean air and water. So that's what my research comes to do. So the feedstock I'm starting from is wheat straw. It's in pellet form. And then I have 3 sets of experiments. So slow pyrolysis on its own, which is the traditional way of making charcoal. I'll use different temperatures between 400 and 600 and different residence times. Another set, which is slow pyrolysis and physical activation using steam or CO2. And then another set with slow pyrolysis and chemical activation using KOH as the chemical agent. This with the objective to create the final solid product, which will potentially have fast and efficient removal of an organic contaminant from water and potentially to overall clean water. So I'm doing this in the experiments in an auger reactor, a screw reactor, in which you can feed biomass through a vertical tube we can see on the left, and then the screw can push the material along horizontally, and the solids are collected in the char pot. The screw can be controlled with a motor. You can control the speed, and temperature is also monitored and can be controlled. The vapors from pyrolysis go through a cooling and liquid collection system. You can collect different fractions of the liquid, and the uncondensable gas goes through a filter and can be analyzed. And then to apply the chars, I have a stock solution of methylene blue in water. I start with 100 milligram per liter concentration. This is a typical organic dye used in research when you're applying chars or adsorbents to clean water. So it's used by lots of research groups. This is an example of my char. The char is also in fine particle size of around 400 micrometers. So I take a small amount of it and I mix it with an amount of the stock solution for 2-3 hours, also controlling temperature. And then you get this result. These are different test. So on the left is the starting stock solution, has more or less a very dark blue color. And then depending on the efficiency of your char, you'll remove the blue and eventually get a clear water in the end of the mixing. So then to measure the final concentration of the methylene blue in solution, I use UV visible spectroscopy. So start off with some results from slow pyrolysis. I saw the usual trends of char yields decreasing with temperature and at the expense of gas. This is an example for solid residence time of 3 minutes. And this table is the overall trend for all 3 residence times. So temperature is the most, this is the parameter that mostly influences the process, not as much more than solid residence time. And we can see the trends existed in all the experiments. So, but to sum up, char yields decreasing with temperature, gas yields increasing, and there's a maximum of liquid yield around 50% produced at the experiments from 500 degrees at all solid residence times. So, and then I tried to simulate a steam atmosphere in the reactor by increasing the feedstock moisture content to 50 or 75%. And I did these experiments at 400 and 600 degrees. And the results I obtained at 50% moisture content were very similar to the ones with the normal feedstock. But the ones produced from the feedstock with 75% moisture content got a decrease of about 5% in char yield, which was very interesting. And I also did an experiment, like a control experiment with oven dry wheat straw to see if the yields of char would change. And I did not see this effect. So I only saw an effect for the feedstock with 75% moisture content. So then the chars, for analysis, I grind them and sieve them to around 400 micrometer particle size, as I mentioned. Doing proximate analysis with temperature, you see a decrease in volatile matter and an increase in fixed carbon content, which is usual, was expected. And there wasn't much difference between the normal chars from just the as received feedstock and the chars produced from the feedstock at elevated moisture. In terms of the elemental analysis, there were some differences. So for 400 degrees, there was a decrease in the carbon content with the chars from the elevated moisture content feedstock, and an increase of the oxygen content. And this was not seen for the 600 degree experiments, and this is quite interesting, and other analyses were performed. Nitrogen porosimetry, I found very low surface areas all around the chars I produced, so I'm not increasing porosity, at least with the simulated steam experiments. I'm still doing the other sets of experiments, so I don't have those results yet, but I'll hopefully have them soon. So very low porosities for all the produced chars. And in infrared, I saw, of course, as expected, a great decrease in chemical functionalities on the surface, and especially for the char produced at 600 degrees has even less than the other chars. Then comparing the chars from the different moisture contents in the feedstock, is the 400 degree ones are in the blue lines, and then the red lines or orange lines are the ones produced at 600 degrees with different moisture contents. So we can see that the functionalities compared with the feedstock are greatly reduced still, but there is an increase, especially noted for the chars at 400 degrees, of an increase of, for example, the double O bonds and the C single O bonds, and this is indicating that something happens on the surface of the char, and this will probably relate to the adsorption performance, and will hopefully improve it. So some results from the liquid phase adsorption of the methylene blue. I had like a control test with activated carbon, which removed almost all of the dye, 99%. And then I saw this interesting trend, which was the chars produced at lower pyrolysis temperature were more effective at removing the dye. So I got around over 95% removal, which is comparable to the activated carbon. And then the efficiencies for chars produced at higher pyrolysis temperatures were decreasing. So only got around between 50 and 60% dye removal for the chars at 600 degrees, and even with the oven dried, the char derived from the oven dried feedstock. And then the chars produced from increased moisture content feedstock. There was no change for the 600 degrees pyrolysis ones, but for the 400 degree ones, there was a slight increase, which made the efficiency even closer to that of activated carbon, which was what was desired from the experiment. So we saw this positive effect at the experiments at 400 degrees with increased feedstock moisture. So then I'm conducting the other sets of experiments with chemical activation and physical activation with CO2. And I will be analyzing and testing those chars as well, and hopefully there will be some more differences and improvements, maybe. So for some conclusions, summing up what I've shown you today, the experiments where I changed the moisture content of the made a difference in the char yields when the moisture content was 75, and didn't make any difference when it was 50. So, and this had possibly an effect on the quality, on the performance in absorption of the chars. Through the analysis, I found very low porosities for all the solid products that I produced so far. So it seems that the steam that was developed in the reactor was not effective for the activation, probably because temperature was low. Usually these experiments with steam activation are conducted at least at 700 degrees, which is not what I'm doing. But I found an increase in the removal of the contaminant, which is good. So using char from slow pyrolysis alone I can effectively remove the dye, and I saw even an increase in that absorption, as I said, from the chars from the wheat straw with increased moisture content. And it seems that it's the surface chemistry, the chemical functionalities, that seem to play the biggest role in the absorption performance, and it's not porosity. When you're looking at gas absorption, you want to use an activated carbon, and you want very high surface areas, which can be over 1,000 square meter per gram. And in this liquid phase application, it seems that it's the surface chemistry that's making the dye binds to the surface of the char. And so the functionalities on the surface are much more relevant. And it was seen, so the increase in the absorption performance is probably related to the increase in the surface functionalities I saw through the infrared. And that's possibly explaining why the absorption performance increased. But this needs further analysis of the chars and trying to explain what's happening in the absorption, the mechanism, and why it relates so much to the surface chemistry. And then testing the chars I'm producing with the different activation procedures for the absorption experiments, and then looking at ways to regenerate the adsorbents I'm using. So if you want to scale this up or you want to do this industrially, it's very important that you can recover the solid you used. And this can be done with a thermal treatment, for example, and it needs to be efficient and relatively economic, so you can have a good marketable product. So I'm also looking into ways of doing this, and also investigating if there is any leaching from the char products into the water. So I may be removing the dye, but maybe I'm introducing other things into the water, which is not very useful. It's not the objective. So I'm also going to be investigating this, and also other possible things that are happening contributing to the adsorption mechanism. So that's my presentation today. Thank you for listening. If you have any questions, send me an email or you can ask questions now. Thank you.